In your computer science, well, I mean, you obviously went on to PhD, to go into that field in computer science. What were in that day, in that time, what was the difference in computer science than you see today? Because I think if there's one field in the last 50 years that has advanced the most, it would be computer science. Right. So what's the difference like?
One interesting thing in theory is stuff that people were interested in then nobody even knows about or studies or cares about today, including the work I did my PhD thesis in.
Can I get an example of that? Because I'm just wondering, just to pinpoint.
So, for example, here's something something false that I often see theoreticians say, that we have no explicit examples of functions that require exponential time to compute, or no natural examples of languages where membership requires exponential time to compute. And the fact is there are lots and lots of examples. People just forget about them. And it's that work with my advisor, Albert Meyer, that I was working on at the time, proving that certain languages require a lot of time to compute. What we can't do most of the time is get the computational complexity right to within an exponential. We tend to be off by an exponential. So there are plenty of languages I can prove require exponential time to compute, but the problem is they probably really require double exponential time. There are languages I can prove require double exponential time to compute, but they probably really require triple exponential time. So we're just off by an exponential. That's one thing people don't talk about very much. Examples of these languages. They come from logical theories. The second order theory of one successor, for example. They come from mathematical logic. Another thing people used to talk about a lot are various types proving certain results about special types of Turing machines. For example, in what sense can we prove that a Turing machine with two-dimensional tapes cannot simulate well a Turing machine with one-dimensional tapes? Things like that.
Interesting.
Or Turing machines where tapes have many heads versus one head. Things like that are just subjects that nobody cares about now. And this is within theory itself.
But I think, if I may, and I think this could be, that it's advanced to such a degree at this point that people completely forego the basic fundamentals, right? Because people are immediately thrown into program hello world. They're not taught how that hello world is actually programmed in the first place and what it takes when you type in the words print hello world or whatever, right? So I guess, could that maybe be a reason? Because it was so fundamental back in the day, there was just a lot more to learn about the fundamentals. And
one of the interesting things about the theory, the basic open questions of computational complexity, such as does P equal NP, are there one-way functions? There has been zero progress since the 70s. Zero. Absolutely zero. Minus 273 degrees centigrade or whatever. Zero progress in that. What we have made progress in theory is using assumptions to do more and more interesting things, particularly in cryptography. So we can use assumptions to do more and more interesting things. But as far as the validity of those assumptions, no progress whatsoever. So you're more interested, I think, in issues involved programming. And I will say this. People no longer believe the things we were constantly being told. When I was young, we were told in programming languages that declarations are very, very important. And it's very important to have declarations, and it's a very rich thing. That now we're taught, Python's perfectly good. You don't need declarations.
Exactly.
So the practical people don't seem at all concerned about the fact that they change their minds all the time. And I find the practical stuff there very frustrating because there doesn't seem to be any constancy or anything. Just things keep changing.
Well, they just do whatever's convenient, right? Whatever works.
Well, that's the trouble. Do you really? Yeah, of course. If you don't have to declare stuff, that's one less statement, and so you can write your program more quickly. But surely we're concerned about your program's being correct and right and everything. And I would think we need even more declarations. This is my field, of course, more types of declarations. You need for example, units. You want to know about what units things are in. So especially for a physicist, let's say you're writing a program and you have all sorts of different things. You would want, you can tell me if this exists, by the way, if you know, you would want the syntax to check your units. So, for example, if you define the gravitational constant in certain units, and if you have a force is g m1 m2 over r squared, and you'd want that to come out to the correct units. Right. And the syntax of your language should check that your units are correct.
Right. I don't know if that's actually being done, but I know that there are packages in Python that do keep track of your units. So you just you assign units to some of your constants and variables, and you can do the calculations, and then at the end you ask, okay, what are the units of my answer, and it'll give you the units so you can check to see if it makes sense or if you made a mistake somewhere.
So I'm asking that be done all automatically.
Right.
And not only units in that sense, but also units, we're talking about metric or imperial units. It wasn't that long ago where mistakes were made that way. And it can be very costly.